Oh, there we go. Now you should be able to hear me just fine. I don't think I need a microphone boost, however. Let's pop on the stream to make sure that you can hear me alright. Today's video might be a bit on the shorter side and is going to be concerning oh no, apparently we do need Okay, hopefully now you can hear me alright. Today's stream is going to be there, a little bit better. And I can turn myself a little bit down as well. So today's stream is going to be concerning a new idea that I had about the revolution of the finger. And the test case per se is going to be revolving around the Protosonho case again. Technically their case is testing the solution that we made on Monday, but I also want to test a new way of making this joint right here. So I'm gonna do this in 2 steps. Step number 1 is going to be making a new file completely in which we test how this would actually look naturally. So without having all the nice and biological curves, having just the very basic geometrical shapes to see if this actually works. If we manage to get it done in another file, we will try to modify this version of the Phoenix hand to put it at least on the second finger right here, on the index finger, and see how it works. It might work, it might not, we'll see. Okay, so basically the idea that I had was based on something called the fractal vise. So this is a fractal vise. I don't know if you've ever seen anything like this, but basically it has a lot of smaller plates connected as a tree structure, if you're familiar with programming. It's basically a bunch of hemispheres placed inside bigger hemispheres. And because these are free floating, meaning that they can rotate freely without any friction, or with as little friction as possible, that also means that you're just fine with not having the axe as physical. What I mean by that is, if you have the rotation axis of something, doesn't really matter what, if the rotation axis is inside the object, that doesn't matter if it's actually connected, as long as it's inside the object. For example, if I have a circle like this and that's rotating as a disc, so let me show you the axis. There you go. If it's rotating around this axis, this is technically a normal rotation axis. However, if the object doesn't intersect the axis and it doesn't surround the axis completely, so for example, if I have something like this, now this is what I call a virtual rotation axis, because the object doesn't surround the axis and it doesn't intersect the axis either. So it's basically rotating around something that's outside of the object. And this is what I want to try on this case. Basically, I want the rotation, because it doesn't have to surround the axis and it doesn't have to intersect the axis. In our case, this can be the finger and this one can be the natural axis of the knuckle. Because you can't surround the entirety of the human knuckle because, well, basically because you have to cut through the hand if you would do that. And you can't really intersect the normal axis of rotation. We have to use a virtual axis. And the virtual axis would be somewhere around here, instead of being all the way up front over here. If it works, it should give the user a much more natural feel to it. It might not work, however, so we'll see how it goes. Alright, so those are the basics behind the idea. I'm gonna pop it off on the second screen. And let's change the music to piano or this sounds like more fun. Right, so let's make a finger, well, the base of a finger with a virtual axis. How should we approach this? I have not thought this through. Okay, we're gonna delete everything. And let's say we are looking at the object from the right side. And this will be our virtual axis. So technically our hand would be something like this. There you go, so that would be our hand. Let's give it a dimension, because why not? 4 centimeters seems reasonable. And we don't care how much this goes backwards, because there is no way we can put something behind it, because people have arms, not just hands. Okay, so let's see, we would have to have a finger. So we can use an arc with a center point. So let's say this would be the finger. And this line is virtual. And that's not that's not symmetric, is it? Oh, there you go, now they're connected. Okay, so basically for all intents and purposes this is going to be our finger. Now this cannot be connected because we have a wall over here. So basically, this being the normal hand with the knuckle, we also have the walls of the device. And we have a frontal wall and we have a wall down there. So let's say the walls are 5 millimeters thick, which is quite thick, and then we can have this system right here. Let's see how this looks. Okay, the fingers are a bit on the heavy side, so we might want to make them smaller. There you go. And if we assemble it, oh, we need to make components out of them. I want to see them moving. So this is going to be the hand, this is going to be the finger, and if we tap on our keyboards on A, we can bring up the appearance from over here, and we would have, let's say, red plastic. There you go, so our finger is red. So if we press Shift J, we're gonna have this one with this one being the master, and the joint type is going to be revolute around this axis. There we go, so now we have achieved movement. Hooray! We have a minimum and a maximum, and that's minus 90 degrees. There we go. So now we can animate the model. And looking at this, we can start figuring out how the mechanics of it should actually be working. Which is a tougher thing to do than, than to say. So right off the bat, I noticed that this ending right here is going to be an issue. And to showcase that, this is the lines of the device. Let's say the device only goes to around here. Fantasy medieval music instrumental. That's a very, very random music I found. I hope you like it. Alright, if we finish the sketch... Wait, no. I would like to have this higher up. And that's gonna be the device. So if we go with extrude, and it's gonna be a new body all the way to over here, and this is going to be black plastic. Can I have that? Thank you. Right, we can make the sketch invisible. So as you can see right now, they are not touching, but we will need to have them touching. So by the looks of it, when we animate the model, we're going to have two major issues. Number one is that it's going to try to go inside the device right here. And number two is that it's going to try to go inside the device right here, because of these very small corners. So, question is, which one do we need to treat as an absolute limit, and which one can we work around? So I think the lower one has to be an absolute limit, and let me show you why I think that. If we bring this all the way to over here, well, plus a very, very small offset, it needs to go at the very least 90 degrees. Now, when it goes 90 degrees, this is going to intersect the device quite a bit, and the device is already quite thick, so it might actually end up trying to intersect the hand itself, which obviously it cannot do because it would hurt the user. So this side of it needs to be straight. So let's see how we can fix that. Going back into the sketch. This looks like a nice point. Of course, I'm exaggerating here, but it's important to go from the middle. And there you go. Now when we drive the joint, it won't try to go inside of the hand. And this space, in order to not have that little pokey corner, we need this line to be at the very center of the object. This space, however, doesn't need to be quite so big, so we can go even as little as this. This doesn't have any issues. It could theoretically be perfectly straight down. Actually, why not? Let's make it all the way down. So now when we extrude that, it's going to be without a corner. There you go. So now it's not trying to poke holes anywhere. So that's one side of it, and that needs to be absolute. However, when we go up, this one can technically intersect the plastic part. because the plastic part only needs to be around the finger. So in this case right here, if we cancel the selection and we select this face and look at it from the right side, this is the space that's allocated for the hand. In actual real life, the hand is only going to be something like this, and when it's being pushed down, it's going to be something rounded off right here. Weirdly enough, these fingers are actually quite big for the user's hand. So technically, all of this plastic that's above this is just to let the user be comfortable and flop around inside, and to have enough plastic to, well, do nothing with it really, because that's just a lot of plastic wasted on the idea that you have to surround the wires, and you have to have a big system right here. The most of this bulk of the plastic is ensuring that it has a giant hole in the middle for this part to go into. So it's not technically unused space, however it's not really used either. If we figure out how to cut this in half to only use this part, then this part doesn't need space, and it doesn't need space over here either. You can bring it all the way back. So as you can see, most of this plastic is technically wasted. Of course, having a tighter fit on the hand also means that you need to be much more precise with your measurements in real life on the user, and you might need to print more tests to make sure that it fits properly the user's hand. Looking at my own hands, it's also going to be an issue with the big finger, with the thumb, but that can be solved. Right, so in theory, there is nothing stopping us from making this line somewhere higher. Technically, through this space you only need to have a wire passing through, and the wire needs about a 1 millimeter space. Let's say you have a bad printer, you're gonna need about 2 millimeters of space, which is, this particular one has 5 millimeters width, so you have 1.5 millimeters on each side plus a 2 millimeter gap in the middle, which should be more than enough. You can theoretically shave some of that off as well. Okay, let's see how this looks. Yeah, this looks alright. And up top over here, you don't really need all of this space because it's gonna be a tighter fit. So if we start rotating this, yeah, that looks quite alright. So up to the next issue. Next issue being, how the heck are we going to have this part not fall off? So how are we going to connect the device that's holding the palm to the finger itself? And for that I'm getting inspiration from the same source. Meaning the same fractal vices. Let me see if I can find a picture that exemplifies nicely how they are actually connected. Well, there is none. Isn't that nice? Oh well, that's too bad. We're gonna have to model it from scratch. So basically the idea is to have kind of a dovetail connection. So how should we try to design this? This is going to be a bit more weird, of a design. And I've just spotted another issue. The idea is to have something like a dovetail design. Let me show you what I'm talking about. So this is going to be rotated around afterwards. So on this side we have the hand, on this side we have the finger, and we would have something like this. Let's make them collinear. There we go. Whoops, I forgot to do something. Right, so if we revolve this part around this axis, let's say 270 degrees, and then we revolve the other side for, let's say, 90 degrees. So technically this would be our finger. Basically the hand would be over here somewhere, and this would be the connection, and this one would be spinning around within this slot. Issue being, let's see if it even is an issue. Shift J, revolute, and the snapping point is going to be this one. Minimum, maximum, and the rest. And the rest is going to be right here, because that's the normal position of the finger. Can move down to here. Right. So theoretically we would have this movement. So the finger would be pointing on to the right side and the hand would be to the left side. However, this movement is not quite what we need, because the dovetail is intersecting the device, meaning that this design is not possible because this part is straight. Okay, so we can be allowed to have this part straight. So if we rotate this one, okay, I need lofi. I can't focus on this kind of music. Sorry about that. So question is, how big is this going to be? So I think it's about time we played with some real numbers. So this part appears to be 25 millimeters. Now we could do this in geometry, and traditionally I would make a bunch of geometry just to make sure what formula do I get for this little height. However, this is Fusion 360, so we can use the power of the software in order to not really care about how things are done on the inside. The radius of this is 9 millimeters, meaning that the entire finger is about 18 millimeters tall. Okay, so this thing only needs to be about 20 millimeters. Okay, that's not too bad. And this radius right here is 40 millimeters. The space that the original user of this made. Let's see, can I inspect from over here to here? Yes, nice. So, oh, so the space inside such a cuff is only 30 millimeters. That's quite a bit smaller than I imagined. Actually, let me measure my own hand. I'll be right back. Right, so I have my own Schubler right here, and measuring around the widest part of the knuckle is only 23 millimeters, so using 30 millimeters as a measurement is going to be more than enough. Okay. Let's say this is still 5, and the offset between these two, because, well, things cannot be perfectly flush with each other in real life, let's say the offset is 1 millimeter. Okay, and if we drive the joint all the way up here and we make a sketch right here, what is this height? We're gonna project this line. To hit project, just press P on your keyboard and select any other line from your design, or a face if you feel like it. Hit OK. Now this line right here is 1.5 millimeters. So theoretically we would be going like so, and offset without the chain selection 1 millimeter, because that's the offset on the other side as well. So we would have to cut this little triangle off completely. Let's see how it looks. And to make sure that we're only cutting the black object, we're going to deselect the finger. There you go, so now it can actually work. Theoretically. And the leftover piece right here of plastic is 170 millimeters, so we had to cut off more than half, which is not too bad really, because we can start cutting off from this side as well. So we could be doing something like this, for example. So when we extruded the original piece, we could go without the corner, and this way we wouldn't even technically be intersecting. No, these are not connected. So when we deleted this, that's not too bad. And that's with real measurements, so we wouldn't need to take off quite that much of the material. Okay. This is surprisingly good so far. And on the top side we don't really care, we can get this as big as we want to. So over here we could be, actually it doesn't really matter, because this is already as wide as it needs to be. Okay, time to redesign this entire thing using this geometry, which we can just don't save it. Question is, how hard will this be to print and to mount, really, because it's not gonna be something very easy to mount either. Huh. Actually, I just realized something. No, it doesn't work. I was thinking of having the finger come off on the top. So literally disconnect from the hand so that we can 3D print the entire finger as it is. Let's see, what kind of dovetails can we use for a rotation motion? So one obvious dovetail is something like this. In which case this would be the hand, this would be the finger. So the hand would be surrounding the finger. And the other option for a dovetail, well, of course we have the other one. So we have this version as well, where the finger is surrounding something from the palm. We could also do this with something like a pillar. So for example, if we can have something like this, which is also possible. Question is, which one is going to be easiest to 3D print, because that's going to be quite an issue. So we're gonna have all of them spin around this axis. There seems to be an issue. Oh, there we go. This is supposed to be collinear with this and with this. So now we can revolve 1, 2, 3 around this axis. Let's go with 180 degrees. And now we can revolve the fingers around this axis again, and we're gonna go with 90 degrees this time. And new bodies. So technically the hand needs to be the hand needs to be something like this. Actually, it's gonna be 45 degrees because it needs the finger to go all the way down and all the way up over here, which is gonna be about 45 degrees from the top where the line actually ends. So which one is easiest to print from these three scenarios? For the hand, this one, for example, is completely excluded, and this one, because this one would need to print in midair. Oh, it wouldn't, because you could have the hand continue at this level. So this would be just bridging two sides. And I haven't joined Discord or shared the stream. I guess that's quite alright. But I might as well share this too. This is quite an issue, because we have to 3D print the finger as well. And there is also the question of which ones of these designs will be the most reliable when you actually have a lot of weight on it. Well, technically from the finger side of the issue, all three possess no real advantage as long as these sides are fairly big. So it doesn't really matter. So it only matters to be as small as possible, so that means we're not gonna use the fur design. So we just have to decide between these two designs. Should the hand be like this or like this? Now, when choosing this part, what it matters most is how do we actually mount it. As in, how do we connect the finger to the hand? And for that there are two options. We can either have the finger cut in half, so cut in half lengthwise like this, and being mounted each side, and then connecting the two sides, or we can have this part continuous, and the rail would be ending right here, so as the finger revolves it will just get off the rail. Pretty much how curtains are actually designed to go on a rail. It's really the same principle. It's just that we have solid corners instead of normal rollers. I think for the sake of simplicity, I like the third option best. It's gonna be a little bit ugly, but I think we can deal with that. So we're gonna modify this part to not have this one, and we're gonna create a new sketch on the bottom right here. Whoops. Well, firstly we need to move this back, so we're gonna have this at 0 degrees, capture the position, make a new sketch, and this is this the right sketch? Because of lighting it doesn't look like this side is quite as big as this side, but they're both 1 millimeter. I think this is the right one. Whoops, I meant to keep editing that. So use the slice option, and let's start making a giant dovetail. Now firstly I want to make this as wide as a finger, so if we are measuring a finger's width, we might as well measure from here to here, which appears to be 21, so we're gonna make it 20. So when we extruded this originally, we're gonna have it like so. There we go. So now when we actually make this sketch, is going to be to size on both the height and the radius, which is really important. Okay, so let's project all three. Well, we're gonna have to project the bodies. That's quite an issue, so we're gonna have to work with what we've got, because we can't project this slice for some reason. So technically we have this thing right here, which is, we know it's 15 by 20. Then we have this part, which we know it's 5 by 20. Then we have a rectangle that's 1 millimeter by 20. And then finally we have the finger, which doesn't really matter for the height, but we have the width as 20. And we can move all of the measurements up here and down here to get them out of the way. And now we can make the bodies invisible. There we go. So now we have a pretty good idea of what is what. We can't intersect this part. We have to leave about 2 millimeters anywhere. So over here we're gonna have to have about 2 millimeters everywhere, and in the middle we're gonna need to have about 4 millimeters of headspace, and that's simply because this is where the wire is going to be. So in the middle of this 4 millimeter headspace, actually we're gonna have a small rectangle of 2 by 2, and the middle of this is going to be connected to the middle of that. We're gonna make this line perpendicular, and this side is going to be 1.5 millimeters. So this way we know for certain that it's straight in the middle, and that's gonna be the space for the wire. And we're not allowed to cross this line on any of the sides. Now we want a profile that is as small as possible, so we could have, whoops, that's not the right way. This is, we could have something like this, and this is technically just construction lines. No, actually this is not a construction line. We have symmetry between this one, and this one. Let's say this is 45 degree. Actually we can make it a 60-degree one. And we should have the three sides pretty much with the same dimensions, so this looks about right. And this distance is 5 millimeters. So we have 5, 5, and believe this is, I have no idea what that measurement was. So what's the distance between this point and this point? 10 millimeters, and then another 5. Let's say this is gonna be 6. Nope, 5 it is. And then we need to offset everything by probably about half a millimeter. But for that, firstly, we're gonna need to make this offset about half a millimeter, which is done from over here, 0.5. And now if we go over here, this one needs to be 0.5 as well. Okay, so the finger is simply going to connect to these parts. Okay, let's cancel the body and all of the bodies to make them invisible. There we go, that makes them parallel. These two are mirrored as well around this. These two the same. Actually, we don't need this. So actually I'm just going to delete this line. There we go, that's fixed. And to offset everything, we need this point connecting to this line. And this one as well. And this is going to be 0.5 millimeters. Oh, this is not properly mirrored, so this one is mirrored to this one. Oh, okay. We have symmetry between these two and the middle one. It's still moving up and down, so let's make a line right here that's gonna be purely construction and connect this one. There we go. So oh wow, this is messing with my brain. Okay, let's see if I got this right. So these parts are the finger and these parts are the normal thingy. Okay, that looks decent enough, and in reality this offset right here is gonna be distributed through everything else. So there is no need for other offsets. Okay, and now comes the fun part, because we're gonna have the finger and the body, which is technically a component called palm holder. And we're going to be extruding quite a bit of the palm holder. So we're gonna have those whoops, that's a revolute that was supposed to be. And the space for the wire, and the axis of rotation is going to be this one. Okay, we need about 100 degrees. Nope. 110. Yeah, 110 looks reasonable. It's gonna be a bit on the small side over here, but that doesn't really matter. And Now we need another rotation from the third sketch, whoops, from the second sketch as well. Which is going to make space for the finger to get out. So it's going to be I should have done this the opposite way. Ah, that's perfectly fine. So we need to revolve this part around this axis that's still connected to the bottom right there. Yep, that's perfectly fine. And the finger technically never reaches more than this. So we have plenty of space to pull the finger out if we really want to. And this part can be completely uncovered because the hand is right here. It doesn't get taller right after your knuckles. So we have plenty of space to actually pull the finger out and put a new finger in if we really want to. Okay, and let's connect the finger as well. I want to check something, however, over here. Yeah, technically this shouldn't be able to pop out on its own. So we're gonna use revolve again for these two parts. Make the... it's gonna be two sides around this axis. And this side is going to be like so. Well, technically it doesn't need to be quite that much. Let's say like that, and this side needs to be just as big as the finger. We don't need anything fancy. Okay, let's see if the modeling is right. Okay, so that's intersecting a little bit over there. Let's see why. So we're gonna be manually rotating it. Okay, I can see why. So we're going to put in the last one and take this back. Let's say 18 degrees looks decent. 17? 17 is nice. So the finger is connected strongly. And yep, it doesn't even intersect. So the finger is moving right now nicely while still surrounding the natural axis of the knuckle. Oh, and we are pretty much up on the hour. This is perfect. Okay, no messages, no nothing. The only thing that this would be technically lacking is a space for the cable. Now, because the cable is quite so weird to say, on the side, on the original sketch, we're gonna have a little bit of dedicated space for the wire. So I think the wire can be coming in right here, and we've said that we want to have something that's 2 millimeters wide and goes all the way through. Whoops. If we move this down, let's say it's at the very least 1.5 millimeters left underneath. So that seems fair enough. We can have a small hole like that, because we only care about the middle phalanx right here. So if we extrude on the initial design, this is the space for the wire. We're gonna have it symmetric of 1 millimeter, so the entire hole is going to be about 2 millimeters. Whoops. One side offset, the offset is going to be -10, well, -11, and then this one is going to be 2 millimeters, so that's going to be the wire. There we go, that's where the wire pops in. And we need a space for the wire to flow over this. We have a space on the inside, but we don't have a space yet on the outside. For the space on the outside, we're gonna go with something really simple. A 2x2 thingy right here. That is going to be placed right in the middle. So if we extrude this upwards all the way to, let's say, here, we should have been, yep, it connected nicely with the internal geometry of this thing, which is just perfect because the wire can come in from the top, from the device, it goes all the way down, and then it will have a small slot over here on the outside. Let's model that slot right now. We're gonna make the body invisible. Where do we need that slot to be? Oh, we need a small slot right over here. And let's say it's gonna be 1 millimeter by 2 millimeters. Which, now that I see it, is quite quite an issue, because we end up with a very small wall over here. Actually, in order to not to have a better view over this, we're gonna have a section analysis of -10. There you go. So now we can see the insides and how the cable runs. Why is this? Weird. In any case, so the wire comes from the top, goes all the way to the bottom, and should have a small channel until it gets to up here. And to model that small channel, no, yes, this is the one. We would be going without this space. Oh, that creates a channel upwards. No, that's perfectly fine. We're gonna create a new channel from scratch. We need to make the finger invisible. That's gonna be revolved around this axis up to here. Okay, and we don't need this to be a full 1 millimeter. 0.5 millimeters is gonna be more than enough. We can technically have this being 6 millimeters, so we can have this wall even bigger. There we go. Something weird happened. Oh, okay. No. Not this one. Oh, we are looking upside down. Okay, that makes more sense. I was wondering what was so quirky about it. So on this one we actually need this to make two sides. And also get this over here. Oh, whoops. Actually. Okay, I'm starting to have no idea what is... oh, this is intersecting right there, so there is an issue with the sketch itself. So when I made that 6 instead of 5, it didn't duplicate to the red one. So we need offsets from over here. This one needs to be 6 as well. So that's what happened. Okay, now it's not intersecting anymore. And we can modify this to be two sides. Can we? Oh, we don't need to. Yeah, we just have a small offset over there, caused by the fact that we're still using... Huh. That's too big of an offset. I genuinely have no idea what's going on and why this is such an issue. So that's fine. Oh, that's the intended offset. What is wrong with me? That's 0.5 millimeter right here. So from this space to this space, yeah, the distance is 0.5 millimeter. We actually designed that and I forgot that I've already put it in the design. Okay, we can have this entire finger smaller. There is no need to have it that big. And there you have it. This should be pretty much on size. And I will need to print this and see if it mounts correctly, and hopefully one day this will actually become a functioning finger. Of course, it's quite a number of ways to get modified until then, but this seems quite a good starting point. Oh, we should probably modify this. There we go. I'm just playing right here, doesn't really matter what I'm doing. Anyway, this is the design, and this has been today's idea. I will see you all tomorrow. I'm not sure about the the specific time, but we'll see. And I believe tomorrow we will be dealing with either a new thing for the collab meeting, or it might be something else. We'll just have to wait and see. But thanks for joining, and I will see you all tomorrow or in the next video, because probably nobody's gonna join anyway. Thanks for watching, and see you on the hub.